The atmosphere is a gaseous envelope that covers the Earth. The atmosphere extends from the Earth up to 1,000 nautical miles. Without the atmosphere, there would be no life on Earth. The atmosphere provides protection from harmful ultraviolet or UV rays, cosmic rays, and meteorites. The atmosphere also protects the Earth from extreme temperature variations. It supports animal and plant life through its gaseous content and provides rain to grow crops. The envelope of air that surrounds the Earth varies in pressure and temperature throughout its entire height. There are 4 distinct divisions of the atmosphere. Each has its own special characteristics that separate it from the others. The first division is the troposphere. The troposphere ranges from sea level to 30,000 feet at the North and South Pole to 50,000 feet at the equator. The egg shape is due to the cooling and heating of the Earth's surface. The main characteristics of the troposphere are declining temperature with altitude and water vapor which produces weather. This is where the majority of aviation activity takes place. The tropopause is a small region of temperature stability that forms the boundary between the troposphere and the stratosphere and is not considered a major division. The next division is the stratosphere. It extends from the tropopause up to 50 miles. The stratosphere has a relatively constant temperature, little water vapor or turbulence, and contains the jet streams. The next level up is the ionosphere. It ranges from 50 miles to 600 miles. It gets its name from the ionized gas within this layer. The ionosphere provides protection from ultraviolet rays. The 50-mile high mark is known as the Van Karman's line. Above this line, aircraft controls become ineffective and thrust must be used for directional control. The final major division of the atmosphere is the exosphere. It extends from 600 to 1,000 miles. Past 1,000 miles, we are officially in space. As we ascend in the exosphere, we gradually approach the vacuum of space. There is so little pressure and density that gaseous molecules rarely collide. An artificial environment to sustain life is required. The atmosphere is a mixture of gases. It is composed primarily of nitrogen and oxygen, along with trace gases. Nitrogen and the trace gases are inert gases which play no major role in human physiology. For this discussion, we will ignore the trace gases and consider nitrogen as 80% and oxygen as 20%. A key point to remember is that as we ascend to altitude, the percentage of nitrogen and oxygen remain constant. If the functional percentage remains constant, why do pilots, skydivers, and mountain climbers have trouble at altitude? There is a drop in atmospheric pressure. The gaseous atmosphere surrounding the Earth is affected by the gravitational pull of the Earth. Atmospheric pressure is defined as the combined weight of all atmospheric gases creating a force at any given point on the surface of the Earth. In 1924, the U.S. Weather Bureau and the Bureau of Standards set forth a group of values to measure atmospheric pressure. The true weight of the atmosphere at sea level on a standard day is 14.7 pounds per square inch. This standard atmospheric pressure can also be expressed in several different forms depending on the method of measurement. If measured in millimeters of mercury, the standard pressure at sea level is 760 millimeters of mercury. This is the height in millimeters that a column of mercury will rise in a vacuum tube when subjected to the weight of the atmosphere. When measured in inches of mercury, the sea level standard is 29.92. This is the height in inches that a column of mercury will rise in a vacuum tube when subjected to the weight of the atmosphere. This measurement is what is used in our aircraft to measure our flying altitude. As we ascend from sea level, the atmospheric pressure will drop. As the atmospheric pressure drops, the air becomes less dense. Let's review the laws that explain the effects of reduced barometric pressure and how it affects the human body at altitude. Boyle's law states that a volume of gas is inversely proportional to the pressure exerted on the gas, with temperature remaining constant. As a high-altitude balloon is taken to altitude, the pressure drops so the gas within the balloon expands. If this gas is not vented overboard, the structure will rupture. This happens to humans going to altitude, and we have ways to equalize this trapped gas. Trapped gas will be discussed later. Henry's law reads, when the pressure over a liquid is decreased, the gas in the liquid will also decrease. The nitrogen in the body is in gaseous form. If a person goes to altitude where the pressure decreases, there is the possibility that this nitrogen will come out of body fluids and tissues and form bubbles. The physiological disorders of decompression sickness and evolved gas disorders will be discussed later. Dalton's law tells us that the total pressure of a mixture of gas is equal to the sum of the partial pressure of each gas in the mixture. As we ascend to altitude, the total atmospheric pressure will decrease because the partial pressure of the individual gases decreases. Remember, the percentage of oxygen at altitude does not change, but the partial pressure does. This decrease means less usable oxygen, which causes hypoxia. Hypoxia will be discussed in a later section. Graham's law states that a gas will diffuse from an area of high concentration to an area of low concentration. This law explains the transfer of gases, mainly oxygen and carbon dioxide, between the atmosphere lungs, lungs blood, and blood body cells. Another way to classify divisions of the atmosphere is from the point of view of the physiological effects on the human body. There are three major physiological zones. The physiological efficient zone ranges from sea level to 10,000 feet. Generally, the body is adapted to operate in this region, but because we have the ability in an aircraft to ascend and descend rapidly, and this is the area of the atmosphere where the greatest amount of pressure change occurs, trapped gas problems, for example ears, sinus, and GI tract, can occur. In addition, shortness of breath, dizziness, headaches, and fatigue will occur if a person is exposed too long in the upper region of this zone. The physiological deficient zone ranges from 10,000 feet to 50,000 feet. The majority of flying takes place in this zone. Inadequate oxygen, atmospheric pressure, and cold temperatures do not allow for normal physiological functions in this zone. The space equivalent zone extends from 50,000 feet to space. This environment is very hostile to humans. An artificial environment produced by a full spacesuit or a sealed spacecraft is required. Both of these provide their own gases and pressure. Above the Armstrong line at 63,000 feet is where body fluids boil. We will wrap up this lesson with a short review. The atmosphere is a gaseous envelope that supports and protects all life on Earth. The atmosphere has four distinct divisions: troposphere, stratosphere, ionosphere, and exosphere. The atmosphere has decreasing pressure with increasing altitude. All gases act in accordance with the physical gas laws. There are three distinct physiological zones: physiological efficient zone, physiological deficient zone, and space equivalent zone.